Hello students, a very warm welcome. Today we'll be taking up gaseous state and we'll be taking up the first lecture in that, which is I'll be introducing you to some parameters and we'll be talking about some properties of gases. So let's begin. Great. The first slide. Talking about gases. Gaseous substances possess very small particles and these particles can be either atoms or they can be molecules, right? You know water vapor, right? H2O. H2O can exist in a gaseous form, that is water vapor. So molecules, as you've seen, can also be gases, right? Atoms can be gases in gaseous form, right? Okay, so this is the first point. Talking about the second point, these particles remain far away from each other and maintain their continuous motion, right? They are continuously moving, right? Because there is a lot of free space, they can keep continuously moving and they are very far away from each other, right, in comparison to solids or liquids. All right, I'll move on. Secondly, the motion of such particles is called Brownian motion. All right, these gaseous particles, if they are placed in a container, right, they are placed in a container, what they'll be doing is they'll be moving in all directions, right? They can move like this, they can move like this, they can collide with the walls, they can collide with the walls here, they can collide with each other and so forth. So this kind of zigzag motion is called Brownian motion, right? Okay, so gaseous particles show Brownian motion. Great. The next point, the gas do not have definite volume and definite shape. So these gaseous particles, that is atoms or molecules, if you place it in a cylinder, it will take the form, if the cylinder is closed, it will take the form of the cylinder, right? They will fill the cylinder completely. If they are, let's say, placed in a cone, right? This cone is also closed. They will fill the cone completely and the volume of the gas will be equal in this case to the volume of the cone, right? So they don't have a definite volume and a definite shape. Whatever the container you fill them in, take the shape of the free space in that container. Or if the container is completely empty, then it takes the shape of the container itself, right? Great. I hope you've understood. I'll move on. The next point, the gases exert pressure equally in all directions. This is very important, all right? This is a very pertinent point because let's say we have a container which is filled with gases, all right? Let's say these are the particles, all right? So when this particle comes in contact with this particle, whatever the direction of contact it is, they will exert the same pressure. For example, if this particle collides head on, right, at 90 degrees with the head of the container like this, all right, the pressure will be same. If it collides like this, even in that case the pressure will be the same exact value, right? So remember this, gases exert pressure equally in all the directions, right? Great. Apart from that, you must have heard about atmospheric pressure, which we'll be talking about in detail in today's class as well as in the next class. The atmospheric pressure, because of the gases present in the atmosphere, the atmospheric pressure is also exerted equally in all directions, all right? I'll get to the next point in the meantime. Okay, the density of the gas is very low due to the gas molecules are present in the large space. Because the particles are small, they have generally less mass, and what happens is it occupies the entire container or entire free space, so the volume is a lot. So that's why we know that density is mass upon volume. So mass is generally less and volume is higher, so that's why density is on the lower side. All right, I hope it makes sense. So the density of the gas is very low due to the gas molecules present in a large space, right? We are talking in context of the volume over here. Okay, the next point, they are highly compressible, all right? So for example, if we have a container which is filled with gas, right, and this is a piston system, all right, if we exert, initially it will be in equilibrium state. That means this pressure would be equal to the pressure exerted by the gas on this container wall, right? All right, but if we press the piston down, we exert more pressure over here. What will happen is the volume will shrink, right? The piston system, the entire system will move down, right? So these gas molecules will become compressed, or they will apply lesser volume on application of pressure, right? Pressure, volume and temperature are the three things we have to play with. They are the three parameters of importance over here, and we'll get to them one by one. All right, okay. The next point that I want to talk about with you, the gas expands on heating, right? So this is very simple and intuitive to understand. You know that gas expands on heating. In fact, anything expands on heating. What happens is when you apply temperatures, for example, let's say in a container, you have a gas filled, right? This is the wall of the container, and you have these gas particles over here. And if you put a burner over here, if you put a burner over here, what will happen is these gas particles will become more energetic, right? You're supplying energy from outside, they will become more energetic and they'll collide much more fastly with each other, right? Much more abruptly with each other. They will exert more force, right, on each other as well as on the container wall. So the container wall will, what happen is, it will go up, right? It will go up. So that is, the volume will increase, or it will expand on heating, in other words, right? I hope you've understood. The next thing, very important, the gases may be liquefied at high pressure and low temperature. So if we increase the pressure, what will happen? On increasing the pressure, the particles, the interparticle distance will become very less, right? So generally, you might be knowing that these gas particles have intermolecular force of attraction which is very less, right? It's van der Waals forces. What are van der Waals forces? We'll be talking in the chapter of chemical bonding. But over here, if we increase the pressure, what will happen is the particles will get closer, right? They will get closer, due to which what will happen is their volume will reduce, and when you make the temperature low, right, you take out the energy from the system, they will become much more stable. So what will happen, instead of being a gas, they will become a liquid, right? So this is the property of liquid, right? Liquids have lesser intermolecular distance and a greater interparticle attraction. So that is to say, these gases will behave as liquids, or in fact become liquids, when the pressure is increased and the temperature is reduced, right? All right. Kinetic energy of ideal gas is a function of temperature only. So what happens when we increase the temperature? When we increase the temperature, the energy in the system increases, right? The energy in the container in which the gas particles are contained will increase, right? Due to which the velocity will increase, right? And when the velocity increases, what happens is that the kinetic energy, because kinetic energy is half mv square, right? So kinetic energy increases. In fact, we can just say that kinetic energy is a function of T, of temperature, right? In fact, it comes out to be 3/2 nRT, where N is the number of moles, R is the gas constant. It's the gas constant, all right? I'll talk about its values soon. And this is the temperature. Temperature in Kelvin, right? Okay, I hope you've understood how kinetic energy is a function of temperature only, and it follows this formula. Kinetic energy is 3/2 nRT, where N is the number of moles, R is the gas constant, and T is the temperature in Kelvin. Alright, I'll move on. Okay. Next, we'll talk about some parameters of gases. Alright. First of all, the mass and the amount of substance N, right? Amount of substance N, we're talking about the moles. So this is moles, right? And this is the given mass, right? So we've already seen the formula in earlier chapters of physical chemistry when we were covering mole concept, that the number of moles is the given mass, which in this case is given to be W, right, over the molar mass, right? N is the number of moles. What was molar mass? Molar mass was the mass of 1 mole of a substance, right? 1 mole was 6.022 into 10 to the power 23 particles. The particles could have been anything, right? In chemistry, generally atoms, molecules, and ions, right? So whenever we are talking about moles, we are talking about 6.022 into 10 to the power 23 particles. The next thing, this molar mass, as you might remember from our previous lectures, that molar mass is A grams, right? Where A is the mass number. I hope it makes sense, guys. All right. So this is the first parameter that we've talked about, mass, right? With respect to amount of substance, right? The amount of substance with respect to mass. I hope it makes sense, guys. I'll move on. Secondly, the three parameters that are very, very relevant over here are volume, pressure, and temperature. We are first talking about volume over here. All right. Volume, the space available for movement of gas particles is called volume of a gas. All right. 1 mole of ideal gas at STP conditions. You know what STP conditions are? 0 degree centigrade and 1 bar. This is the modern STP that you must remember, right? And the old STP was 0 degree centigrade and 1 atm, right? But we're talking about 0 degree centigrade and 1 bar over here. That was 22.7 liters, right? By 1 mole, right? 1 mole of an ideal gas at old STP, which is 0 degree centigrade and 1 atm, the volume of 1 mole of an ideal gas is 22.4 liters, right? And hence we came to this formula, if you remember from our mole concept lecture, that the number of moles is the given volume given over 22.7, right? At the modern STP. At old STP, it will be divided by 22.4. I hope you understood this, right? So, gas, as you know, takes the shape of the container or the shape of the free space in the container that it is in, right? Now, this is about the ideal gas. What is an ideal gas? This is a very important question, and since we are in the chapter of gaseous state, we'll talk about this. So let's say there is a gas in a container, right? And these gas particles are so small that their volume is negligible, almost zero. In that case, we can say that our gas is ideal gas. And not only that, the force of attraction, the intermolecular force of attraction between the gas particles must be zero. So, volume of individual particles. Pay attention to the wordings, guys. Volume of the individual particles is zero. The volume of individual particles is zero, not of the entire gas. This is something that you have to pay attention to over here. Secondly, force of attraction between particles is also 0. So that means volume of ideal gas is actually equal to the volume of the container, right? But this is not the case when we are talking about real gases. All right. In case of real gases, the particles occupy space, right? So for a real gas, the volume of gas will be equal to the volume of container minus the volume of particles, of gas particles, right? So this is real gas, right? The volume of real gas. For an ideal gas, the volume of gas is equal to the volume of container, but that is not the case for a real gas. I hope you've understood this basic difference between ideal gas and real gas. Moving on, we'll discuss some units of volume. First of all, 1 decimeter cube is 1 liter. Secondly, you might be knowing 1 liter is 1000 ml. Thirdly, 1 ml is 1 centimeter cube. Alright. Also, now that we know 1 ml is 1 centimeter cube, 1 liter will be equal to 1000 centimeter cube. Alright. So these are the few units that you must remember. Okay. SI unit of volume is meter cube. Alright. 1 meter cube is equal to 10 to the power 3 liters or 1000 liters. Alright. Or conversely, we can say 1 liter is 10 to the power minus 3 meter cube. Right. This conversion is very simple. You just have to know all these, and you have to know that 1 meter is 100 centimeter. Right. I hope it makes sense, guys. Do remember the units. If you cannot recall the units during your exam, then it will become a big trouble for you, and you will not be able to get to the right answer. Alright, there might be confusing options. For example, similar answers but differing in the number of zeros or the number of zeros after decimal or something like that, and you will get confused and mark the wrong answer. So remember the units, it's very, very important. Alright, let's do the basics correctly. Alright, moving on. So we spoke about the first parameter, which is volume. Now we'll get to temperature. Temperature, the basic definition, it's a measure of hotness or coldness of a body. It affects the kinetic energy. And we've seen the relation that kinetic energy is 3 by 2 nRT, where n is the number of moles, R is the gas constant. This is the gas constant, we've spoken about this as well. Its value is 8.314 joule per Kelvin per mole. Alright. For the ease of calculation, sometimes you can take it as 25 by 3 joule per Kelvin per mole. Right? In calories, when we convert joules to calories, it will become 1.987 calorie per Kelvin per mole. Alright. Remember, from this gas constant itself, because we are taking temperatures in Kelvin, this T is the absolute temperature or the temperature in Kelvin. Alright. When we are talking about gas laws, for example, if we are talking about Charles' law, you must have studied that previously. Even if you have not studied, we will be covering that in detail. Whenever we are talking about temperatures, we are generally talking about absolute temperatures. And when we are expressing the relation with degree centigrade or degree Fahrenheit, I'll tell that to you separately. Alright. I hope you've understood. Alright. So kinetic energy is a function of temperature only. We've discussed this before and we're discussing this now. Alright. Now talking about the units of temperature, the SI unit of temperature is Kelvin, right? K, represented by K. Then comes degree Kelvin is related to degree centigrade. Degree Kelvin is not referred to as degree Kelvin, it's just referred to it as Kelvin. So I'll just say temperature in Kelvin is related to temperature in degree centigrade like this, right? To obtain the temperature in Kelvin, we just add 273.15 to degree centigrade, or if we have to do the converse of it, that is obtain degree centigrade when Kelvin is given, we can subtract 273.15 from that, right? Thirdly, degree centigrade is 5 by 9 degree Fahrenheit minus 32. So three units of temperature popularly known: Kelvin, which is the SI unit, degree centigrade, the most popular unit, and degree Fahrenheit as well, right? So these are the three relations that you must remember. All right. I hope it makes sense, and I'll move on to the next very important parameter, which is pressure. Pressure. Force acting per unit area is called pressure. Pressure is defined as pressure is force upon area, right? The gas induces a pressure inside the vessel because gaseous particles show molecular motion. What that means is, because they are always in continuous motion, they collide with each other, exert force on them, because of this which there is a pressure exerted, and they also exert a pressure on the container walls, right? So force is induced due to this motion, and that is why pressure is exerted. So force is pressure upon area, right? A very simple notion. Force is induced due to this continuous motion of gas particles, because of which pressure is exerted. So pressure is force upon area, that you might be knowing already, right? Moving on. The next thing we'll be talking about is the units. I'm clarifying the units in the initial chapter because you need to understand that it's very important to remember the units, right? So I'll move on. So first, SI unit of pressure is Pascal. It's represented by PA, right? The second unit is 1 atm that you should be knowing about. 1 atm is 1.01325 into 10 to the power 5 pascals, right? The third unit that you should know is 1 bar. 1 bar is related to atmosphere atm, right? It's not atmospheric pressure, right? This atm is not atmospheric pressure. The atmospheric pressure at a certain time can be equal to 1 atm, but this 1 atm is a unit. It's not atmospheric pressure. I hope you understand the difference, right? Another unit that you should be knowing about is bar. 1 atm relates to bar as 1.01325 bar. 1 atm is 1.01325 bar, right? So just this 10 to the power 5 gets removed, right? And we get the bar unit, right? If we convert bar into atm, 1 bar will be equal to 0.987 atm. All right. Please remember these units. Apart from that, one more relation that you should remember is that 1 atm is 760 mm of Hg, mercury, or 76 centimeter of Hg in the barometric column, right? What's a barometer? We'll be talking about soon, right? You just have to understand that in a barometer, mercury rises, and when the mercury rises to 760 mm in the barometric tube, that is called 1 atm. So you should remember all these units very, very thoroughly. Moving on, we'll talk about barometer and how we calculate atmospheric pressure. All right. Atmospheric pressure, the atmosphere, right? For example, let's say we have placed gas in this container. All right. If this lid of the container is not moving, right, that is, it's an equilibrium. That means this pressure will be equal to this pressure, because the gas particles inside the container will be exerting pressure on the container wall, right? But it is not moving, right? So that means something is balancing it out. What is that something? That something is the atmospheric pressure, right? What the surroundings is exerting on our system, right? So the atmospheric pressure. How do we measure atmospheric pressure? We measure atmospheric pressure using what's called a barometer. All right. So what we do in a barometer, we have a vessel, right? A dish in which mercury is placed. Mercury is placed in this dish. All right. And then there is a column, a vertical column, very narrow vertical column, in fact, right, which is dipped like this in this mercury, right? So what happens is, because there is atmospheric pressure exerted over here, this mercury rises up this tube, right? And let's say it rises, let's say, up to this level. Mercury fills this tube up to this level. So in that case, the atmospheric pressure, not 1 atm, atmospheric pressure will be described by the height of mercury in this column. All right. So 1 atm is equal to 760 mm or 76 centimeter of Hg, right? But the atmospheric pressure at certain instant can be greater than 1 atm, it can be less than 1 atm, or it can be 1 atm. So atm is just a unit, right? So you've seen how we can measure atmospheric pressure using this barometer. I hope it makes sense, guys. All right. I'll move on. So as we've seen, barometer, it consists of inverting a narrow glass tube, right? This point is very, very important over here. The glass tube is narrow, right? It's a capillary tube, a narrow capillary tube through which, right? Because if it was too wide, right, for our purposes, what will happen is that it will not be able to rise up to the specified benchmark, right? So our measurements will not be correct in that case, right? Because if it grows horizontally also, right, the vertical, the column, it grows horizontally, there is much more space to grow, go horizontally. What will happen is that it will not be able to rise up to a proper level, right, and we will not be able to measure the mercurial column, the height of the mercurial column. I hope you've understood, guys. I'll move on. So it's placed or dipped in a vessel or a dish of mercury, and due to the atmospheric pressure acting on mercury, this mercury rises up. Wherever it sees the space to go up, it just climbs up. So it climbs up the narrow column, and hence we get the height of the column, which we say is the atmospheric pressure at a certain instant, right? I hope you've understood, guys. I'll move on. The last slide that we have is that pressure due to liquid column, or what we call hydrostatic pressure, hydrostatic, water, right, or liquid, right, and it's static, right, it's not moving, it's not in motion, right? So hydrostatic column, the pressure depends only on the height of a particular liquid in the container. All right. So for example, let's say there is a container like this, right? All right. And then there is a container like this, right? different shapes again filled with something, right? Thirdly, let's say you have a container like this, right? If you're talking about the same heights, let's say we are measuring the pressure over here, and over here at the same heights, right? Then the pressure would be the same, right? Why is it the same? Because pressure is force upon area, right? Force in this case will be the force exerted by the liquid which is above the this point in the container, right? So it will be mg, right, where m is the mass and g is the acceleration due to gravity, which is 9.8 meter per second square, right? And then there will be area. Now let's say we multiply both the numerator and denominator by the height, this height, right? We multiply it by the height. Then in that case, what we'll get is we'll get mgh over ah. And we know, I'll write it over here, we know that ah is nothing but volume. So this will become mass into g into h over volume. And we know that mass over volume is density, right? So this will become density into g into h, so rho gh basically, right? So this will be the pressure at any height in a hydrostatic column. It will be rho gh. Rho is for a particular liquid, right? It's different for different liquids. So if the liquid is same in all shapes of the container, then the only differentiating factor will be the height, right? If the heights are the same and the liquid is also the same, the pressure would at that point would be the same. All right. So we've covered this very interesting topic of gaseous state, right? We've started with it. We've introduced some parameters and we've talked about properties of gases. All right, we'll be continuing with some other topics, for example, Boyle's law, Charles' law, and all in the next lecture. All right, for that, you'll have to wait, and I'll see you the next time around. Bye.